Math 2414, Sequences, Video 3. More examples, alternators. Actually, we're going to do one example and talk about alternators, which is a term that I coined when teaching this class, but it's a phenomenon that shows up regularly. In fact, it shows up in this particular example. We're going to find the explicit function an for the following sequence. Pretty jacked up sequence. We start with 3e to the third over 5. And the next term is negative 8e to the fourth over 25, followed by 13e to the fifth over 125, then negative 18e to the sixth over 625, and then the fifth term is 23e to the seventh over 3,125. All right, there's a lot going on in this sequence, but the trick is to look for patterns in individual pieces. For example, if you just focus on the denominators, it appears that, I wanted that to be red. You focus on the denominators, it appears that this is a geometric sequence with a common ratio of 5. So we already know how to deal with that. When the ratio is 5, and the first term is also 5, and again, this is just in the geometric sequence in the denominator, then we know exactly how to set that up based on what we saw in a previous video. I'm leaving some space in front, you'll see why in a moment. But to write the explicit function for a geometric sequence, it is the first term, which is 5, times the ratio to the n minus 1 power. And right away, I immediately want to multiply these together by adding their exponents and just get 5 to the n, which we'll do in a moment. Let's focus on the numerators, specifically the coefficients of the e's. Now you'll notice that these coefficients are alternating in signs: positive, positive, negative, positive, negative, positive, and presumably the next one would be negative. But we'll worry about the pluses and minuses in a moment. Let's focus on the 3, the 8, the 13, the 18, and the 23. If you focus on just those, it won't take you too long to determine that those form an arithmetic sequence. 3, 8, 13, 18, and 23 all have a common difference of 5, with a first term of 3. And again, I know the signs are alternating, but we're going to handle those individually, or separately, I should say. So how do we write the explicit function for an arithmetic series? Well, we take the first term, which is 3, and we add the common difference 5 times n minus 1. And in a moment, we'll distribute the 5 and combine like terms. Let's catch all that in parentheses for a second. And one thing real quick, I meant for this down here to be in red, to be consistent. 5, come on, draw. 5 times 5 to the n minus 1. And again, we're going to simplify this once we get it set up. But let's focus on the e for a second. The powers on the e, 3, 4, 5, 6, 7, are technically an arithmetic sequence with a difference of 1 and a first term of 3. So we could do the same thing we did for the 3, 8, 13, 18, and 23. But when your arithmetic sequence has a difference of 1, there's no need to overthink it, because what we're asking is, what do we do to the n to get the number that we want? Keeping in mind that on the first term, n equals 1, on the second term, n equals 2, and so on and so forth. And really the big question we're answering is, what do we do to the n to get all of these different terms in the sequence? Well, if you'll notice, the exponents on the e, which start at 3, are all 2 more than their position in the sequence. In the first position, the power is 1 plus 2, which is 3. In the second position, the power is 2 plus 2, which is 4. In the third position, the power is 3 plus 2, which is 5, and so on and so on. 4 plus 2 is 6, 5 plus 2 is 7. So it looks like to get the exponent on the e, all we have to do is add 2 to the current position. Now you could also argue that the e's form a geometric sequence, because how do you get from e, what's the ratio of e to the 4th to e to the 3rd? E. What's the ratio of any 2 consecutive e's? E. So we could play the geometric sequence game there as well, but again, if you just have powers of a common base and they're going up by 1, then you just have to shift your n from 1 to whatever it needs to start at. In this case, get from 1 to 3, we just have to add 2. All right, so now we've got everything. Just lost a piece of the problem. Now we've got everything except the signs. So how are we going to make the signs occur? You could almost think of the alternating signs by themselves, positive, negative, as a geometric series, geometric sequence, 1, negative 1, 1, negative 1, whose common ratio is negative 1. But if all you're trying to do is adjust the signs, then all you have to do is take negative 1 and stick a power on it. Now, that power should either be n or n plus 1, depending upon whether your terms start positive or negative. If we put in 1 right now, negative 1 to the first power is negative 1, which means we'll create a negative first term, which we don't want. So we have to bump the exponent up so it starts out even. We could do plus 1 or minus 1. Let's do plus 1. And now when we put in n equals 1, we'll get negative 1 to the second power, which is positive 1, makes the first term positive. And as the n increases, so does the power on the negative 1, meaning that we'll alternate between positives and negatives. Let's clean this up as much as we can. We have the alternator in front, negative 1 to the n plus 1. And again, the plus 1 is to make sure that it starts out positive when we start with n equals 1. In the fraction downstairs, we can add the exponents to get 5 to the n. Inside the parentheses on top, we can distribute the 5 to get 5n. Then we'll have 3 minus 5, which is negative 2. And then we have e to the n plus 2 power. So I want to embed a bunch of different sequence issues in here. Geometric sequence, arithmetic sequence, a sequence of powers that are just going up by 1. You just have to adjust the first one so it starts at the correct value. And what I call the alternator. So I'm going to highlight what's the best looking answer, in my humble opinion. There are some ways to manipulate this to look a little bit less sloppy by combining all the exponents and doing a little bit of shenanigans, but we're not going to worry about that. As long as you can capture each changing piece of the sequence, whether it's an arithmetic, geometric, or something else, then you're okay. But I want to talk a little bit more about what I call alternators. An alternator, honestly, is just a sequence that alternates between 1 and negative 1. So really, it's just a sequence. Now, it could start with 1, or it could start with negative 1. And it's not uncommon to see what's called an alternating sequence, where the signs alternate between 1 and negative 1. So if we have an alternating sequence, how do we make it alternate? Well, we've kind of already answered that question if you go back and look at our previous answer. When you raise negative 1 to a power, its answers will alternate between 1 and negative 1. So an alternator that starts out positive is negative 1 to the n plus 1 power. And the way you know you have to add 1. In fact, let's set off both of these. You know, these are both negative 1s to powers, but the trick is we need to make sure it starts out the correct sign. In other words, when we put in n equals 1, we should get the first correct first term. On the top one, right here where I'm about to highlight, if we put in n equals 1 right now, we get negative 1 to the first power, which is negative 1, but the first term is supposed to be positive 1. So if your alternator should start out positive, you have to slide the exponent up by 1. Excuse me, that's not what I meant to do. You have to translate the exponent by 1. so that when you put in n equals 1, the exponent is even. Now, we could also do -1, the n minus 1, because if we put in n equals 1, then 1 minus 1 is 0, and anything to the 0 power, any non-number to the 0 power is 1. So either one of those would be good alternators if you need to start out with a positive term. But let's take a look at the second one and see if it's what we want. Second one, -1 to the n, does that start out correctly? Remember, the first term is when n equals 1. The answer is yes. When n equals 1, -1 to the first power is -1. So this is the correct alternator to start out -1. Now, there are other alternators besides these. They're a little stealthy, and usually people just use them to be cute and everything. But another common alternator is an equals cosine pi n. And the reason it's an alternator is if you think about the unit circle, and you start with n equals 1, which is pi, which is a half revolution, cosine is the x-coordinate, and so it would start out with -1. But when you bumped it up to 2 pi, you would pick up another half circle, semicircle, and that would make one complete revolution, and over there, the x is equal to 1. By having n times pi, bumping up the n basically just says go another half circle, another semicircle, and you're alternating between 1 and -1. Now, as is, this starts out with -1. If you wanted it to start out with +1, then you would just need to change its beginning by throwing a negative on it. There are other ways to do it, but that would be an alternator that would generate alternating signs starting with +1. So whenever you see -1 to a power in a sequence, its purpose is to alternate the signs between positive and negative in the individual terms. And vice versa, if you see a sequence that has alternating signs, then you can expect its explicit version to have some sort of alternator inside of it to cause that alternating signs.